Energy in SHM then. Clearly there are two types of energy, kinetic, which I'm calling E subscript K, and potential, which I'm calling E subscript P. We know from GCSE and previous work that kinetic energy is a half mv squared, and from earlier on in this work we know that V is minus A omega sine omega t. The minus, of course, we explored earlier on in the course. So if we look at the graph here, the graphs in what we're doing is really important. I think possibly the graph work that we do in physics, particularly at A level, is the most difficult aspect of the course. So here's our graph of V against time. So if we put A omega sine omega t in here, then we get an expression that looks like that, a half m there. V squared is A squared omega squared sine squared omega t. Note that is sine squared, not sine of omega t squared. So if you were to plot that graph, and what I'm going to do here is to give you the two graphs together, the velocity and the kinetic energy, you'd get graphs that look like this. So notice the period of this graph in comparison to this one. So there's your graph of kinetic energy against time. We're going to look at two kinds of graphs, against time and against displacement. So there's our kinetic energy. Now, we know that there's going to be a constant interchange between kinetic and potential. If you think about your spring, mass on a spring, or you think about your pendulum, there is a constant interchange between kinetic and potential. With the pendulum, it's gravitational potential. With the spring, it's elastic potential. So if we consider that there are no losses in this oscillating system, just to make life simple for us, by energy conservation then, the energy is constant. So the kinetic energy plus the potential energy at any given moment will give us a constant value, which I'm calling E subscript capital T. So here now we have the two graphs. We have energy against time. So here we have our kinetic energy plot that we saw earlier here. And we have our potential energy plot, which is exactly out of phase with the potential energy plot, kinetic energy plot. So at any given moment, they add together to give you that same total. So it's all here, nothing here. Half and half, giving you the same total value. It's all in potential and no kinetic. And if you consider this as a simple pendulum, then when your kinetic is a maximum, that's when it's going through the equilibrium position, its lowest position vertically. And the gravitational potential is at its highest at the two extreme ends of the oscillation. So you could look at it as a mass on a spring, and the maximum Ke is as it goes through the equilibrium position, and the maximum Pe then at the bottom. So there we have our period graph of energy against time and here we have the two parabolic plots. These are parabolic, not semicircular. You'll see that from the expression later, actually. You'll see that from the expression for energy against displacement. So they are parabolic. So if we develop our argument then in terms of total energy, the maximum energy, kinetic energy, is going to be a half m omega squared a squared. If you look up here, then sine squared has a maximum of 1, and so the kinetic energy will be half m omega squared a squared. And of course, the maximum kinetic energy equals the maximum potential energy. And if you think about a mass on a spring, the maximum potential energy, the elastic potential energy stored in the spring, is a half times the spring constant times the square of the extension, a half k a squared. So those two expressions have the same value. Now, if we were to consider some other point in the oscillation where the extension of the spring is x, where x is less than a, then the kinetic energy would be a half k a squared minus x squared. And that's a useful relationship to have. You can see that your kinetic energy then is a parabola, and so is your potential energy.